Okay, part 6, chapter 29. Just a couple more items. You will recall Gauss's law. And Gauss's law was actually quite elegant because it allowed us to determine the electric field of charge distributions that had a high degree of symmetry. So symmetry was very important. So you might recall, just for a single point charge, if we would want to determine what the electric field was at some distance r away, we could do that by looking at Gauss's law, which stated that the integral of E dot dA was equal to the charge enclosed divided by epsilon naught. So you recall that this circle here, right, meant that we were doing a surface integration, because this really is a sphere, right? So this is this was a Gaussian, what we called at that time a Gaussian surface, which is a sphere of radius r. R is where you want to know the electric field, and you will recall that the electric field in the little patch of area here, dA, and the vector on dA was also in that direction. And so the dot product now, right, this dot product, E dot dA, which is equal to the magnitude of E, the magnitude of the little patch of area, times the cosine of the angle between those two vectors, right? So theta is 0 degrees, cosine of 0 degrees is 1. So again, by choosing your geometry carefully, and if you have a symmetric charge distribution, then Gauss's law was actually quite beautiful, because the electric field is constant anywhere along that Gaussian surface in magnitude, and so the integral became E surface. The surface integral dA is equal to the charge enclosed over epsilon naught. This was nothing more than the area of a sphere. And so then this just became E 4 pi r squared. The charge enclosed is nothing more than this charge Q. And so that's Q over epsilon naught. If we solve for E, and that's just going to be 1 over 4 pi epsilon naught Q over r squared. And we remember that that is the electric field strength and magnitude of a point charge, right? So that's just an example of how to use Gauss's law, right? We also did it for a line of charge and for a sheet of charge, okay? So again, highly symmetrical problems. So there's a similar, I should say an analog to this in magnetism, and so if you look at what is called Ampere's law. Ampere's law said that we have an integral. This time the circle now is not around a closed surface, but around a closed line, right? Sometimes this is called a line integral. B dot ds is equal to mu naught times the current enclosed. Okay, let's see how that plays out now with just a current carrying wire, right? So going back to our example of here's a wire carrying a current. There's a current. Again, this wire extends pretty far in extent in both directions. And the question is what is the magnetic field some distance r away? So if we were to rotate this wire by 90 degrees, that is, now let's rotate it by 90 degrees and have the current coming out at us. Just going to spin that wire around. So current's coming out, and we want to know what the magnetic field is, right, a distance r away. Then what we do is we, just like in Gauss's law, we form what's called an Amperian loop. So here's a loop, here's a closed loop, what is sometimes called an Amperian loop. And we know that the magnetic field is going to be tangent to the circle at all places here, right? So here's the magnetic field at just two places. And we also know that ds, this would be ds along that loop. Here's some ds. And so now if we were to look at that dot product, right? Look at that dot product in the integrand, and we would have b dot ds is going to be equal to the magnitude of b, the magnitude of ds, cosine of the smallest angle between them. So theta now is equal to 0, since b and ds are collinear. Cosine of 0 degrees is 1. So what happens here is the following. I'm going to have to pick this up because I have an 11:30 meeting. Okay, so I will pick this up in a few minutes. Take care. Bye.